For the entire history of electrical power, almost every power plant on Earth has worked the same fundamental way. You take a heat source, burning coal, splitting atoms, concentrated sunlight, it doesn't matter which, and you use that heat to boil water. The water turns to steam. The steam, under enormous pressure, blasts through a turbine and spins it. The spinning turbine turns a generator, and the generator produces electricity. Then you cool the steam back into water and do the whole thing over again, millions of times. That cycle is so old, it predates the light bulb. The basic principle of using boiling water and steam to do mechanical work goes all the way back to the steam engines that powered the Industrial Revolution. For more than 2 centuries, through every advance in fuel and engineering and materials science, the working fluid at the heart of nearly every power plant stayed exactly the same. Water in, steam out. Spin the turbine. China just broke that 200-year tradition. In a steel plant tucked into the mountains of southwest China, engineers have switched on a power generator that doesn't use steam at all. Instead, it runs on the one substance the entire world spends enormous effort trying to get rid of. It runs on carbon dioxide, the gas we blame for climate change, the byproduct of every furnace and engine and power station, the thing scientists are racing to capture and bury underground. China has turned it into the beating heart of a power plant. And the headline number is staggering. This system is reportedly around 50% more efficient at squeezing electricity out of waste heat than the steam technology the world has relied on for generations. So how does a power plant run on a pollutant? Why did this take 200 years to figure out? And what does it actually mean for the future of energy? Let's break it all down. Before we go any further, I have to clear something up, because the way this story gets told online is genuinely misleading, and I'd rather give you the honest version. When people hear a power plant that runs on CO2, they immediately picture giant machines sucking carbon dioxide out of the sky, cleaning the atmosphere while generating electricity. A magic device that fixes climate change and powers your home at the same time. That is not what this is. I want to be completely straight with you about that. This technology does not pull CO2 out of the air. It does not reduce the amount of carbon dioxide in the atmosphere. And it does not burn CO2 as a fuel. You can't burn carbon dioxide. It's already been burned, which is what makes it CO2 in the first place. So what is actually happening here? The carbon dioxide isn't the fuel, it's the messenger. In every power plant, you need something to carry heat from your heat source to your turbine. For 200 years, that messenger has been water turned to steam. What China has done is replace the water with carbon dioxide, a fixed amount of it, sealed inside the system, used over and over in a closed loop. The CO2 never escapes. It never gets used up. It just shuttles heat back and forth, endlessly. Why does that matter? Because it turns out carbon dioxide, when you treat it the right way, is a dramatically better messenger than water ever was. And understanding why requires us to look at one of the stranger states that matter can exist in. You already know the 3 everyday states of matter: solid, liquid, gas, ice, water, steam. Carbon dioxide has the same 3 states. Frozen, it's the dry ice that fogs up a concert stage. As a gas, it's the invisible thing you exhale. But there's a 4th condition, and it's the key to this whole story. If you take carbon dioxide and crush it under enormous pressure while also heating it past a certain temperature, something bizarre happens. It stops being clearly a gas and stops being clearly a liquid. It enters a hybrid state that scientists call supercritical. In this state, the CO2 flows freely and fills its container like a gas would, but it's also dense and packed tight, carrying heat the way a liquid does. Think of it as getting the best of both worlds at once. A gas is easy to push around and compress, but it's terrible at holding heat. A liquid is fantastic at holding and moving heat, but it's heavy and hard to pump. Supercritical CO2 behaves like both simultaneously. It moves like a gas and carries heat like a liquid. That combination is exactly what you want in the messenger that carries energy through a power plant. And it gives supercritical CO2 a set of advantages over steam that are honestly difficult to overstate. First, it transfers heat far more efficiently than steam does, which means more of your precious heat energy actually ends up spinning the turbine instead of being lost along the way. Second, and this is the part engineers get genuinely excited about, supercritical CO2 is so dense and energetic that the turbine it spins can be a fraction of the size of a conventional steam turbine for the same power output. We're talking about a turbine you could potentially hold in your arms doing work that would normally require a machine the size of a bus. And third, there's a subtle but enormous efficiency win hiding in the physics. To make steam, you have to boil water, and boiling water requires a huge amount of energy just to force it through that phase change from liquid to vapor. It's a wasteful, energy-hungry step. Turning CO2 into its supercritical state takes far less energy than boiling water into steam. You skip a giant chunk of waste right at the start. Put all of that together and you get a power system that is smaller, more efficient, and able to wring electricity out of heat that older technology would have simply thrown away. Here's the obvious question. If supercritical CO2 is so much better than steam, why has the entire world been boiling water for 2 centuries instead? The answer is that this idea is not new at all. In fact, it's shockingly old. The concept of using a supercritical CO2 cycle to generate power was first seriously explored back in the 1960s. Engineers in Italy and the United States looked at the thermodynamics and realized this approach could, on paper, outperform conventional steam plants. The math worked. The theory was sound. The promise was clear. And then it sat on a shelf for 60 years. Because there was a problem, and it was a brutal one. To make this work, you have to hold carbon dioxide at extreme pressure and extreme temperature, continuously, for years on end, while it surges through your machinery. And the materials available in the 1960s, and for decades afterward, simply could not survive those conditions. The metals would corrode, the seals would fail, the turbine components would degrade under the relentless assault of hot, high-pressure CO2. The fluid that made the system so efficient was also aggressive enough to chew through the equipment meant to contain it. So the idea remained exactly that, an idea. A tantalizing concept that worked beautifully in theory and fell apart the moment you tried to build it and run it for real. For 60 years, supercritical CO2 power was the technology of the future, and it seemed like it always would be. Cracking it required advances in metallurgy, in high-pressure engineering, in turbine design, and in materials that could shrug off conditions that would destroy ordinary steel. It required someone willing to pour money and time into solving a problem the rest of the world had largely given up on. That part of the story should sound familiar if you follow Chinese engineering. It's a pattern we've seen again and again. The project is called Koten 1, sometimes referred to as Supercarbon Number 1, and it was developed by the Nuclear Power Institute of China, part of the China National Nuclear Corporation, working alongside industrial partners. It's located inside a working steel plant in Liupan, Shui, a city in mountainous Guizhou province in southwest China. And the choice of location is not random. It's central to the whole point. Steelmaking generates staggering amounts of heat. Furnaces run at blistering temperatures, and a huge portion of that thermal energy normally just escapes into the atmosphere as waste. It does no work. It powers nothing. It simply radiates away, lost forever. Every steel plant on Earth is, in a sense, constantly throwing away energy. Koten 1 captures that waste heat, the heat that would otherwise have vanished, and feeds it into the supercritical CO2 system. The hot CO2 expands and drives the compact turbine. The turbine spins the generator. Electricity flows out to the grid, and the CO2 cycles back around to grab more heat and do it all again. Nothing is burned. No new emissions are created. The plant is generating genuinely useful electricity out of energy that was previously garbage. The system was built in 2 units, each producing 15 megawatts. The first unit connected to the grid on December 20, 2025, and ran stably for months. Then, on May 30, 2026, engineers brought the second unit online, bringing the total installed capacity to 30 megawatts. With both units running, China National Nuclear Corporation declared it the world's first full-scale commercial demonstration of supercritical CO2 waste heat power generation, and the largest and most advanced project of its kind anywhere on the planet. And here is where that efficiency figure comes back. According to the teams behind it, the system is roughly 50% more efficient at capturing and converting waste heat from steel production than the steam-based technology that would traditionally do this job. 50% more electricity from the same wasted heat with smaller equipment. Now you'll have noticed this was built by China's Nuclear Corporation at a steel plant, and you might be wondering where exactly the nuclear angle fits. This is where the story gets genuinely forward-looking. The waste heat steel plant is the proving ground. It's the place to demonstrate that supercritical CO2 power works reliably in the real world, in a commercial setting, day after day. But the steel plant isn't the ultimate target. The reason the Nuclear Power Institute developed this technology is that the same supercritical CO2 cycle could one day replace the steam systems inside nuclear reactors themselves. Think about what that would mean. Today's nuclear plants use their reactor heat to boil water and make steam, just like a coal plant does. They just generate the heat in a cleaner way. If you swapped that steam system for a supercritical CO2 system, a nuclear plant could become significantly more efficient and dramatically more compact. the enormous turbine halls that define conventional nuclear stations could shrink. The whole plant could get smaller, cheaper, and more powerful per square meter. And it doesn't stop at large reactors. The engineers behind this project have openly pointed toward a whole family of future uses where compact, efficient power generation matters enormously. Mobile nuclear power sources, reactors small enough to be transported and deployed where they're needed. Concentrated solar power plants, which generate heat from focused sunlight and currently rely on steam. And perhaps most strikingly, space-based power generation, where every kilogram and every cubic meter is precious, and a compact CO2 turbine could be worth its weight in gold. That's the real ambition here. The steel plant is step one. The destination is a fundamentally better way to turn heat into electricity across nuclear power, solar power, mobile generators, and even spacecraft. A 200-year-old bottleneck finally opened. Now, I don't want to oversell this, because part of why you're hopefully here is that I try to give you the real picture rather than pure hype. This is a genuine, significant achievement. The world's first commercial-scale operation of a technology that defeated 60 years of materials problems. That's real, and it deserves recognition. But it's also a demonstration project, and demonstration is not the same as proven at scale. 30 megawatts is meaningful, but it's small in the context of the global power grid. A single large conventional power plant produces dozens of times that. The big open questions now are about durability and cost. Can this equipment survive the relentless assault of high-pressure, high-temperature CO2, not just for months, but for the decades a power plant is expected to operate? Will the maintenance costs stay reasonable? Can it be scaled up and manufactured cheaply enough to compete with the steam technology it's meant to replace? Some energy analysts have raised exactly these concerns, and they're fair ones. A breakthrough that works for a few months in one steel plant still has to prove it can work everywhere, for years, at a price that makes sense. But here's the thing. Every transformative technology starts exactly like this. Small, demonstrated, surrounded by skeptics asking reasonable questions about whether it'll last. The steam turbine itself was once a fragile experiment. The question is never whether the first version is perfect. It's whether the underlying idea is sound, and whether someone is committed to refining it. On both counts, supercritical CO2 looks like the real deal. Step back for a second and consider what this actually represents. Roughly the entire planet's electricity, the power running through the device you're watching this on, is generated by spinning turbines, and the overwhelming majority of those turbines are spun by steam. We have built our entire civilization on top of a 200-year-old method of boiling water. Any improvement to that fundamental process, even a small one, ripples out across literally everything. A technology that's 50% more efficient at recovering waste heat is not a niche curiosity. The world's heavy industries, steel, cement, chemicals, glass, bleed enormous quantities of heat into the atmosphere every single day, heat that represents wasted energy and, indirectly, wasted fuel and extra emissions. If that heat can be efficiently recaptured and turned into electricity, you're getting more power out of the energy you've already spent, without burning anything extra. That's a genuine climate win, even though the system itself isn't pulling carbon from the sky. And if this technology eventually migrates into nuclear reactors, solar plants, and compact mobile power units, the efficiency gains compound across the entire energy landscape. Smaller, cheaper, more powerful generation, everywhere heat needs to become electricity. There's also a bigger pattern worth naming. This is, once again, a case of a technology invented in the West, abandoned as too difficult, and then revived and commercialized by Chinese engineers willing to grind through the hard materials problems that made everyone else give up. The supercritical CO2 cycle was dreamed up in Italian and American labs in the 1960s. The United States has continued researching it, and institutions like the Southwest Research Institute have built their own demonstrators. But it was China that put the first commercial version on the grid. That's becoming a recognizable story in energy and engineering, and it's one worth paying close attention to, regardless of how you feel about it. Here's my honest opinion, for what it's worth. What I find most compelling about this isn't the CO2 angle, even though that's what makes the headline pop. It's the willingness to attack a 200-year-old assumption that nearly everyone else treated as permanent. The entire power industry decided decades ago that steam was simply how you do this, and the supercritical CO2 idea was filed away as too hard. China didn't accept that. They spent more than a decade working the problem until the materials and engineering caught up with the theory. I think the steam plant era is genuinely going to start winding down over the next few decades, and supercritical CO2 is one of the technologies most likely to replace it. Not overnight. The durability and cost questions are real, and the first version will need years of refinement. But the physics is undeniable, and once a better method gets a commercial foothold, the rest of the industry tends to follow whether it wants to or not. The thing that makes me cautious is the same thing that makes every demonstration project uncertain. We won't truly know if this is a revolution or just an impressive experiment until it's run for 10 or 20 years at full scale. But the direction is unmistakable, and the bottleneck that stopped this for 60 years has finally been broken. So here's my question for you. Do you think supercritical CO2 will actually replace steam turbines across the world's power plants in your lifetime? Or do you think steam is too deeply entrenched to ever fully go away? Drop your honest answer in the comments. This is one of those topics where I genuinely want to know which way people are leaning. If you enjoy these deep dives into the engineering breakthroughs quietly reshaping the world, do me a favor and subscribe to Eastern Engine, and tap the notification bell so you don't miss what's next. We break down these stories clearly, without the hype, and there's a lot more coming. Thanks for watching. I'll see you in the next one.